Yes, I would like first to distribute the homework and other material. We have a class here. So if you remember, we started topic number 33, I think, and that is multi-span beams. So we mentioned that missiles, ships, monorail lines, large space structures, pontoon bridges, floating airfields, etc., are actually represented as periodic structures. That means that they are, say, supported at some periodic intervals. Okay, so this interval is L, 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 etc. So here at the very end, we have simple support. So we designate it as SS. And at the end, I also have simple support. But intermediate supports are not simple supports. Please write down. Intermediate supports are not simple supports. They are just supports. And what happens here is, look please, in the simple support at the end, W equals 0, but also bending moment equals 0. Because this element, beam, can rotate like this, can rotate. Okay? Here, in intermediate support, the only conditions that we have is that W equals 0. So that is what is happening. Because beam can deform like this, for example, or it could deform like this. It could deform in many different manners here. But the main thing is that W equals 0, displacement equals 0. Now, this is actually not one condition. Because when we solve the problem, we are dealing, say, when I have two-span beam, like this. Please look at this two-span beam. In this two-span beam, governing differential equation is naturally the same as it is for a single-span beam. Because differential equation does not know about number of spans, does not know about supports, etc. Differential equation is valid in every point of this beam. Governing differential equation is EI, force derivative of W with respect to x, then plus rho A, partial derivative of W with respect to time. That equals 0. So that is for every x and every time interval t. And displacement, that is a small displacement, which is a function of x and t, of spatial coordinate or axial coordinate in time, is represented as a mode shape times e in power I omega t, or if you want sine omega t, or cosine omega t. That is not important. We are looking into harmonic functions. Once we substitute this postulated relationship, or actually it is not a postulated relationship, but something that comes, as we have seen, from separation of variables. We get the following governing differential equation for capital W. EI, forced direct derivative of W with respect to x, minus rho a omega squared W. So that is the same governing differential equation that we had for a single span beam. Then we divide this as by EI and introduce notation rho a omega squared divided by EI equals alpha in force power. So then governing differential equation becomes forced derivative of W minus rho a omega square W. Okay. Then we can solve this governing differential equation for each span. So then we will have, look please, for every span, span 1, we give superscript 1. So this superscript denotes the span number. So W1 means expression of W in the first span. And we have 4 constants of integration. A1, A2, A3, A4 in the first span. So we have A11, A21, A31, A41. And they are multiplied by our familiar functions K1 of alpha x, K2 of alpha x, K3 of alpha x, K4 of alpha x. By the way, I strongly recommend you not to abbreviate this writing, because some students have abbreviated it and wrote it like this: A1, K1 plus A2, K2, etc. So they did not write A1, K1 alpha x, etc. When they differentiated, therefore, they forgot alpha. When you differentiate K1 alpha x with respect to x, you get alpha. But if you write A1, K1, so shortcut, or I would say even some correlation with, I'm not going to spend my time to write everything for you, or for me, or for humankind, or whatever. I'm joking. Or I'm in a hurry. I mean, I don't want to write everything. I understand. Yes, you understand, but you are human and you are making a mistake. I mean, then you are forgetting alpha when you differentiate. So we get, that is first span. And in the second span, then I get A1, 2, A2, 2, A3, 2, and an A4, 2. So in total, we got 4 constants of integration for each span. That means for 2 span beam, we get 8 constants of integration. Eight constants of integration. Now the question is how to determine these 8 constants. We have naturally some conditions to satisfy, and these conditions are divided into boundary conditions and continuity conditions or compatibility conditions. Now, 2 boundary conditions are imposed at x equals 0. At x equals 0, displacement equals 0, and second derivative equals 0. Therefore, I'm writing this 1. Okay. Now, for x equals 2L, So that means at the end of this two-span beam, I also have boundary conditions. And these are two boundary conditions again. W2 of 2L equals 0. And second derivative of W2 at 2L equals 0. So in total, I have 4 boundary conditions. Now I also have continuity conditions. So for 8 constants, I already have 4 boundary conditions. And now I have continuity conditions, which are as follows. W1, because I differentiated between W first span and W second span. So therefore, I must write W1 at L equals 0, and W2 of L equals 0. That is, first span's displacement at L equals 0, second span's displacement also equals 0. These are two conditions, 1 and 2. And then we have other conditions. Yes? Okay, a student asked whether or not I'm finding coordinate for each span. I have one coordinate system that starts in the beginning and continues to 2L. So therefore, for the second span, it starts at L. For the first span, it ends at L. But at this point of meeting of each other, the displacement equals 0. Okay? So what we say there is that such a behavior is not possible. That means that that is a slope. And that is a slope. So there is no slope discontinuity. Okay, we are demanding. You may want to write this. I did not have this. No slope discontinuity. And then there is no moment discontinuity. So then what we have is, look. So we have continuity of slopes. First derivatives equals 0 for the first span's displacement and second span's displacement. And likewise, second derivatives are also continuous. And that is this expression. That is bending moment. Okay, if I multiply by EI, I will get bending moments. But I canceled them because they are equal to each other. I'm talking about uniform beam. So that is continuity of bending moments, continuity of the slopes. So in total, then, we have 8 equations for 8 constants of integration. 8 homogeneous equations with respect to 8 constants. And naturally, we would like these constants, these constants, A1, A2, etc., not to be 0. In order, therefore, homogeneous set of equations to have a non-zero solution, it is necessary and sufficient the determinant vanishes. And that is 8 by 8 determinant. And that is a frequency equation. Now, let us see what happens when we have 3-span beam. For 3-span beam, what happens is as follows. I will have then this, and this. So then I have, look please, I have the same coordinate system. That is x. These distances are L, L, and L. Okay? Then I have W first, W second, W third. So that is A, okay, let me write it down, summation. AJ, KJ, alpha X. Here also, AJ, KJ, alpha X. Here, AJ, KJ, alpha X. But here I have this first span, second span, third span. J from 1 to 4, everywhere. So how many constants do we have? First write down. So we have here 4 constants, here 4 constants, and here 4 constants. Total of 12 constants of integration. Okay. 12 constants. Then I have boundary conditions. W1 at 0 equals 0. Second derivative of W1, it's capital W, dx squared at 0 equals 0. Then I have W3 at 3L equals 0. Then D2W3 dx squared at 3L equals 0. So again, we have only 4 boundary conditions. Because there are 2 boundaries, so we cannot have more than 2 boundary conditions at each boundary. So we have in total 4 boundary conditions. Now, what about continuity conditions? So at x equals L, W1L equals W2L and equals 0. Then W prime at L, W, okay, first derivative, we have to write 1. Dx at L equals dW second at L dx, that equals 0. That is at x equals L, that is 4 conditions. Then at x equals 2L, we have again W2 of 2L equals W3 of 2L and equals 0. Then first derivatives, D2, 2L dx equals dW3 at 2L dx. That equals to each other. And second derivatives, so again, these are 4 conditions. Yeah, here I forgot to write down that is 1, 2, 3, and that is first derivative and second derivative, of course. D2W1 dx squared at L equals D2W2 at L dx squared. Okay. Please add this, 4 should be 4. D2W1 at L dx squared, D2W2 at L dx squared. Okay? And then we have 4 boundary conditions here. So in total, we have 12 conditions. Twelve conditions for 12 constants. Now, any questions here? Oh, this one? Fine. Yes, sir. No, second derivatives do not equal to 0. Because had second derivative equals 0 only, let me repeat the question. Student is asking, do the second derivatives equal 0 at intermediate supports? No, or at least not necessarily. Because if second, okay, so let me see this. Second derivative is equal 0 only if by chance this support is inside, like this. Then second derivative equals 0. But otherwise it does not equal 0. It just supports this span. It supports like this. Okay, pay attention here. It does not penetrate the beam. It supports somewhere at some point, and displacement therefore equals 0. So this can go like this, anyway, but that is it. Okay? So not necessarily. So then we have 12, so determinant 12 by 12 must be 0. 12 by 12. Now if we have, say, 10 span beam, then we will have 10 times 4 equals 40 constants. Is it right? Then we have 2 boundary conditions at x equals 0 and 2 boundary conditions at x equals 10L. Then we have 4 continuity conditions at each of 9 supports, which makes 4 times 9 equals 36. So 4 boundary conditions plus 36 continuity conditions give us 40 conditions. 40. And then what we have to demand is determinant 40 times 40 must be 0. Okay? 40 by 40 determinant must be 0. So this is, of course, very difficult to do, because to calculate, to evaluate determinant, very difficult. Very complex. Okay, to go by these means. So we will now do something else. We will use another route. Okay? In life, often we must learn which routes are complex, not to take them. Okay? In order not to take these routes. So I taught you what is a complex way of solving the problem. And we are not going to go by this way. Okay? Also for 2-span beam it was possible to do that, and okay? So from this point of view, beams and life is the same. You can even say to someone, life is a beam. Okay? Because in life and in beams you don't have to take very complex routes. Okay, now what we will do is as follows. First of all, we will introduce some singularity function. And this singularity function is like this. X minus L, 0. So this is a sign. Triangular bracket says it is a singularity function. Now, triangular bracket says, denotes, coincides with regular bracket if X is greater than L. And it is 0 otherwise. Now, here, okay, so that is a function, we have it. Now, here I have a support. What does this support produce? This support produces some reaction. So please denote some reaction that I don't know. I did not calculate this reaction. I have no idea how much it is. Now, that means that there is this reaction. This reaction produces some jump in shearing force. That we agree with. Say it again? Yeah, but not at this moment. Not at this moment. Now, let us see what is shearing force. So shearing force, of course, is a third derivative times EI. So let us see. Let us write down shearing force in the first span. Shear force in first span. So that is the third derivative, EI times third derivative, as I said. Now that is EI, and then look please, summation, we wrote AJ1, KJ alpha X, and third derivative. Now when I differentiate this, I will get alpha cubed, of course. Yes, when I differentiate each of these K's, I will get alpha cubed. 3 times, then EI. Now let us say A1, A11. So that was third derivative. K1, when I differentiate K1 once, I get K4. Or K0, which is K4. When I differentiate K4, I get K3. When I differentiate K3, I get K2. Okay, so here I will have K2. Then K2, when I differentiate second term, K2. I differentiate K2, I get K1. When I differentiate K1, I get K4. I differentiate once, I get K3. Etc. The third term is A31. A31 is multiplied by K3. So when I differentiate K3, I get K2 when I differentiate once. When I differentiate once more, I get K1. When I differentiate once, I get K4. And here I get K1. So I have K2, K3, K4, K1. So that is this was a shearing force. This was a shearing force in the first part. So shearing force in the first span is this. Now I'm suggesting you that shearing force in the second span will be this expression plus something. And what plus something will be like this. Just paying attention first and later you will write. Later you will write. When I'm passing this term, I'm passing, so if I would have new coordinate systems there, then this K2, K3, K4 would be zeros. Only K1 would stay. So therefore, actually, I have therefore plus this R value times K1 alpha x minus L. X minus L means when x equals L, this is 0, K1 at 0 equals 1, and I will get R value as a jump. So please write down. Pay attention, we just, in a nice manner, got rid of many constants. I just say that I just have additional terms there. So because jump occurs, K1 is associated with value 1 at x equals 0. Plus R minus R. Yes, sir. Again. Last term, this term is only for the second span. This whole term is only for the second span. For the first span, I have this expression. So it says if x is greater than L, this equals 1. Otherwise, it is 0. Otherwise, this does not exist. Yes, sir.
Why you include the x minus L in the a function? Why would it make this?
Oh, why would... I was asked why here I have x minus L and why not x? Because then K1 alpha L will be some value. But I denoted, so that will be some number multiplied by R. But I know that the jump equals R. R equals the shearing, the reaction. The Vy has a jump which equals R, does not equal R times something. X minus L takes care that this, when x, first of all, this term does not exist when x is smaller than L. But second, x equals L, x minus L allows me to have here one value at that point. Yes, sir. I don't understand your question. When I was asked what happens when x equals 12. When x equals 12, this equals 2L minus L, so that is L. L is bigger than 0, so that is 1. So this is 1. And you just substitute here 2L minus L will be L, so you will get some value. I was asked why I'm using K1 function. Yes, K1 function is in order to get this 1 at x equals L.
Designing your reaction force, can you use
Okay, my student asked if I know R, cannot I use something else? I don't know R. I cannot know R. R is not known even now. I just wrote R symbolically, but the value of R is not known to me yet. Value of R cannot be known unless I solve the problem. Probably at the very end I will get the R value. I just denoted that there is some reaction. I did not even mention how much it is. I have no idea. Okay. If I had R, I would not use K3. I would also use K1 because K1 allows that when x equals L, this R stays only and nothing else is there. Because K3 would give me 0. If I had K3 times K3 alpha x minus L, that would be 0 at 0. If I had K3 here, we know that K3 at 0 equals 0. So that would be not helpful. I would like this value to be present there at x equals L when x is a bit greater than L. Just to the very right. Just to the very, very tiny right. More questions. Please ask questions. That is very good when you are asking questions, when students are asking questions, because first of all, we can respond, and second of all, it is more clear for one person who asks and for the other people. My student is asking whether this is primarily for the second span. No, I disagree with this statement. This statement now is good for both spans. Yeah, this expression is good for the second span, as this suggests. That is, when x is greater than L, that it exists. Otherwise, it is not there. So this is for the first span, this first expression. And this is added when I'm in the second. So in the second span, I have the whole thing. And this is then 1. Okay, not necessarily. As I said, generally speaking, in the second span, I have a different set of constants. That is correct. But then I did not write about shearing force, etc. Generally speaking, when I'm solving problems straightforwardly or directly, then I have different sets of constants. That is correct. Now, however, I avoided this need to have different kind of constants. However, I have the same constants, A1, A2, A3, A4, but I also have additional one that I don't know, and that is R. Yes, I, so to say, reduced, as it were, number of constants. However, I increased number of constants in some sense by 1. Continuity equations are satisfied now, totally. I mean, look, please, I will use this W equals 0, etc. I will use. But continuity conditions are satisfied automatically. Pay attention. Once I wrote this expression, it is good for both spans. So continuity condition is already inside, incorporated. Because I wrote at once expression for everything. Yes, I wrote for the shearing force only. But I can then integrate the shearing force and get W if I want. And I will get additional constants. This is a third derivative of W. So if I were to integrate this, I will get 3 more constants. And I will have this 1 more, so it will be 4 constants. So I did not, that is not hocus pocus, so to say. I did not get rid of the constants. I was able to write only shearing force directly. I am not able to write W directly. I will get it very soon. But I was able to write in such a concise manner only shearing force. Okay, I was asked with how many constants I will end up, so let us wait and see how many constants will I have, etc. We will wait. We will wait for that. Any other questions? Okay. If you will have some questions in a minute or in a second, please don't hesitate to stop and ask. So V of x we know. W of x. V of x. So or this shearing force. Now we would like to find W. So W of x, which is corresponding to this V of x, will be like this. Look, please. AJ, KJ. Okay, because that was a result of differentiations, this guy. Okay? So therefore, when I integrate, I will get back the same what I had. AJ, KJ, alpha x. Now this guy, R. Okay? First of all, here I had this third derivative, EI times third derivative. So this EI will come here. Okay? Then alpha cubed and R. Let us check that this expression is correct. So I'm saying that expression of W will be here R, alpha cubed EI, K4, alpha x minus L, x minus L0. And let us check that that is correct. First derivative of K4 is K3. Second derivative of K4 is K2. Third derivative is K1. So in order to get K1, I should have K4. Now what I'm saying is as follows. I'm forgetting this R and alpha cubed EI. I'm denoting it as A5. And AJ1, I will denote just A, AJ. So I will get the following final expression. That is good for everything. A1, K1, A2, K2, A3, K3, A4, K4, plus A5, K4, alpha x minus L, x minus L, 0, singularity function. Yes? Oh, I did not integrate singularity function, so to say. Pay attention. What I said is as follows. This is like a sign which says when x is greater than L, this is 1, and otherwise it is 0. So here there was a sign. I did not integrate, pay attention. I just wrote this expression like this, pay attention. I wrote for the first part only this, for the second part add this. Then I integrated this part. And then I just remember back that this term appears only when x is greater than L. I actually wrote them separately. I integrated, and then I remembered that this is added term, and I remember that x minus L in zeroth power should be there. Okay, student is asking whether, in machine design, we had a different topic totally. I mean, there when I integrate separately x minus L in zeroth power, I get naturally x minus L in first power, etc. But here, it is just, I just show you the formalism of one part and second part. So to say, I did not write, if I would have written force in these terms, then integral of that force would be in higher powers, etc. But here the purpose was just to show that this term appears only in the second part. Nothing else. So what I'm saying is that in the first part you have what you have, and in the second part you have an additional term. This is equivalent of writing this expression separately, and then writing then here add this term. Then I dealt only with this term. Okay? I got this expression, and then I remembered that that is there, and I added this. Maybe it looks a bit artificial, but it is nice. Maybe it looks a bit artificial, but it is, first of all, it's not artificial. It may look at the first glance. When you sit a bit more, you will see that everything is fine. But maybe at first glance it looks like strange that we integrate like it seems that you integrated this but did not integrate this one or something like that. Okay, but we integrate this expression, but this expression appears only in the second part, so I just wrote it. We can actually, maybe there is a rule, f of x, x minus L0 in integral equals integral of f of x, x minus L0. No, this is not, student is asking whether it's the Dirac delta function. No, it's not a Dirac delta function. No, it has nothing to do with Dirac delta function because I already said it is not a Dirac function. So therefore, it has no connection with Dirac's delta function. But it is, your question is well taken. It is very well connected with Dirac delta function. Had I differentiate this function, x minus L0, then I will get x minus L minus 1. That would be the Dirac delta function. So you are just a person who always remembers cousin of someone whom you meet rather than that person. So yes, cousin of this function is Dirac delta function, but we don't talk about the cousin. We talk about this function directly. What about your question? You have no question. Okay. So then we get, look, W of x. W of x is this. So continuity conditions are already satisfied. I mean, look, please. First, look, derivative of this guy naturally, I mean, look, please, derivative at any point can be calculated. So it's a continuous function. Second derivative is also continuous function. All these continuity conditions are satisfied. Because I wrote at one shot expression for W in both places, in both spans. So therefore, equality is satisfied, or continuity is satisfied. What I did not write is W of L equals 0. Because I could not incorporate W at L equals 0 until now. I never used that. I just said that shearing force has a jump. But shearing force has a jump is nothing to do with W itself also being 0. So then I have, look please, two boundary conditions at x equals 0, two boundary conditions at x equals 2L, one